Hi everyone. My name is Fang-Yi Yu. Today I'm very happy to share with my recent work, multi-agent performative predictions from global stabilities and optimalities to chaos. This is a joint work with Georgios. So if we're trying to learn machine learning, we often start as pipelines. So suppose you're trying to design navigation apps. Then you would like to first collect a lot of historical traffic data, and then you deploy your favorite machine learning algorithms like linear regressions, or neural networks, or any other favorite algorithms, and then you have your predictive models that trying to give you the good estimated arrival times of each route. So in this case, the learning process is in isolations. But however, to design a good navigation app, your predictions will eventually convert to decision making. Either you recommend routes to the users and users decide whether to adopt or not, or you instruct your drivers to take certain route or not. In that case, your predictions will go back and affect the data that you're actually trying to predict in the first place. And one way to understand these interactions is performative predictions. That is, if you think the predictions as part of a broader systems, that is, your prediction is going to support certain decisions, then these predictions is going to fundamentally change the distributions of the future data you're trying to predict. So here you are going to have a cycles between your learning algorithm and the societies. Once we observe these phenomena, we can notice that these performative predictions are indeed happens everywhere. Indeed is everywhere. So take the traffic predictions examples. You may try to predict the arrival times of each route. But once you recommend that route to thousands of users, and the user response, those things is going back and affects the traffic data you're trying to predict in the first place. And the credit scores, if the banks are using those credit scores to decide whether to give the loans or not, that predictions is going to affect the abilities of those learners to pay off as well. In the police patrols examples, you're trying to use you're trying to use machine learning to predict the criminal activities in your cities, and then deploy your police using that algorithms is going to induce a new criminal activities patterns due to your predictions as well. The contributions of our papers has twofold. The first one is conceptual. That is, we extend the notion of performative predictions to multi-agent performative predictions. So this is a very naturalizations of performative predictions. And then also corresponding notion called stability, multi-agent performative stable points. And the second part of our contributions is we provide a threshold results on some very simple learning algorithms. We show two things. The first one is once you pick your learning rate small enough or careful enough, you can ensure convergence. On the other hand, if you are not picking the learning rate in the right way, or you have too much influence on the distribution you're trying to predict, then you are going to have the York chaos, or intuitively you are not going to be able to learn. So here's the outline. We are going to first talk about the models and contributions, and then some simulation results to give you some idea what is chaos, what is convergence. Okay, so performative prediction is best understand through the comparison to the standard supervised learning. In the supervised learnings, you have a fixed distributions, and in the training phase, you have a lot of data points that is sampled from these fixed distributions. And then the goals is trying to pick a model at thetas with parameter thetas, and you're trying to minimize the loss of your models against the same distribution D. On the other hand, for the performative predictions, we imagine there is some deployed model of thetas that is already used in the societies. And then your data is going to be sampled from a distributions that depending on the already deployed model thetas. So it will be sampled from distribution maps on theta. So it's called d thetas. And then when you're trying to deploy, you're trying to consider a new model, which we call it the red theta or script thetas. We are going to measure the performance of that predicted models on the distributions that induced by deployed models, that is blue thetas. So you can think of when you're trying to develop a new navigation apps and a new predicted models, you are going to measure the performance of that models on the existing traffic data, which is influenced by the model that you already deployed before. So in this case, the loss is going to depending on your new model, red thetas, and the data is going to be influenced by the old model, red thetas. And one way to understand these performative predictions is through dynamics. So indeed, if your distribution map D is unknown, then it's nature to think of the agents, the learning agents, would iteratively access a samples that is influenced by their previous deployed models. So that is, at time t, the learning agents is going to get the samples from d theta t. And then they try to predict their model from theta t to theta t plus 1. And then we are going to have a circle because in the time t plus 1, you are going to get a new collection of the data and then improve that to a new theta t plus 2. And in this case, we are going to have a dynamics. So in this case, there's two interesting things. The first one is the agent's learning process is indeed a dynamics. So you are going to change your model from theta t to theta t plus 1 based on your previous observations. And an interesting a special models is called, it's the fixed points of the dynamics. That is known as a performative stable points. Points is performative stables as long as once you use that models in the previous run, then the best models in the next runs will be the theta star itself. So this is kind of a stable situation. Once you reach that point, then there's no reason for you to change that to the other models. Another way to understand is this is indeed a game. You have a machine learning algorithm as agents, and these agents is playing a game against himself. That is, once he sees the rewards affected by the data, it's going to choose what models to use in the next round. And the notion of performative prediction have gained a lot of interest in machine learning and EC communities. And there's a long line of work trying to understand the convergence of various of learning dynamics. And it can be roughly classified as two. The first is some simple retraining algorithms, and they show convergence once your problem is convex enough or smooth enough. Then those naive retrainings will be sufficient for to show convergence and good performance. The other line of work is trying to impose various of structures of this distribution map, and once you have the handle of that, then this would be reduced to similar to like supervised learning problems. Our work is trying to understand the first part. So because we are thinking in general, so the distribution map is very complicated because your model is complicated and the society is complicated. So maybe it's more reasonable to think as people are. It's more reasonable to think people may use simple retraining algorithms and trying to see what happens in the long runs. And the motivating question we're trying to answer is, once you use these simple retraining algorithms, when does it fail? So our contributions is saying, so back to our contribution. Well, our threshold results saying that certain kind of these simple online learning algorithms, there will be two phenomena. First one is the retrainings, or these algorithms will work once you pick a small enough learning rate. On the other hand, the learning may fails. That is, the old chaos will happens once you have too much influence on the data distributions they're trying to predict. And the old chaos, we feel free to refer to the papers, is a very classical notions of chaos that shows your learning dynamics will be all over the place and will not have a convergence behaviors. So let's back to the thinking the predictions as the games. We have learning agents, and they're trying to minimize their loss through the interactions with the society and seeing the data. And it will be very straightforward to consider what happens if you have multiple learning agents. And in the navigation example, you can think as, besides Google Maps, you also have Waze, Apple Maps, Ubers, etc., trying to do recommendation or trying to predict the traffic data. And their models are going to be collectively influence the distributions, that is the traffic data, that they're trying to predict. And the notions will be very similar to the performative predictions. In the performative predictions, we have deploy model, the blue data, and we also have a predictive model, the red data. And we're trying to evaluate the predictive models based on the data that is influenced by the deploy models. On the other hand, if we are in the multi-agent performative predictions, the data is going to be influenced by a collection of deploy models. That is, the actual traffic patterns is going to be influenced by all the previous navigation apps algorithms. So here, the distribution maps will be mapping from the collections of models to the distributions. And each agent is going to measure their loss on these historical data. In the performative predictions, a special point is called performative stable points. That is, once you use that models, it will be also best for you to use that models to minimize your performative loss. For the multi-agent performative predictions, you can also define multi-agent performative stable points. That is, for every agent, once your data is going to be affected by the collection of the theta star vectors, for every agent using the theta star I would be also the optimal one for them. So now we are ready to introduce our threshold results. So it's a very simple TOEIC samples, which kind of simple enough for us to understand these threshold results. So first, we consider linear distribution mapping. That is, you can think as this as a linear regressions, and everyone deploy their thetas and try to predict the y based on the features x. And in the linear distribution mappings, the features x is going to be independent of the agent's models. However, the y will be affected by their models. So if and the effect is going to be influenced by the influence parameters lambdas. So you can think as lambda, when lambda is equal to zeros, then the relationship between x and y is indeed a very simple linear relationship. Y will be equal to x in the product with theta zeros. And once the agent's model, once lambda is non-zeros, then the linear coefficients is going to be influenced by the agent's models. So instead of theta zeros, it's going to be influenced by every other agent's models in a linear way. And for the retraining algorithm, we are thinking a very simple algorithm for online convex optimizations called exponentiated gradient descent with a fixed learning rate etas. Okay, so this is like a very simple. You can think it as it's a special case of follow regular speeders with right regularization, with entropy as a regularizers. So in our result, we are thinking a linear distribution mapping and exponentially gradient descent algorithms. And there's two factors. The first one is the influence parameters lambda, and the second is the learning rate etas. And we show a threshold properties based on lambdas and etas. First, if you fix the number of agents n, the influence parameter lambdas, if you take the learning rate eta to be small enough, then the limits of their models is going to be performative stables. So that is, once you fix everything and you decrease your etas, then there will be some points that you can always reach convergence. On the other hand, if you fix your learning rate, but the product of the number of agents times the number of agents times the influence parameter lambdas is large enough, then the Leo chaos will happen. That is, once you have too many agents or your influence is too large, then we can show chaos is going to happen and your dynamic is not going to converge. Thus, you are not going to reach some stable points of your process. So this is indeed a threshold result. For any points, you are going to either have these purple regions or these green regions. And we have a threshold saying sometimes once you pass a certain point, you have convergence. On the other hand, you are going to have a chaotic result. Okay, so the proof idea is quite straightforward. Feel free to read the papers. And to give you some ideas, here is the simulation result. If your learning rate is small enough, we can see the models is actually converging to the performative stable points. That is in our case, it will be a 0.7. And we can see the loss is kind of converging to a very small value. On the other hand, if you have too much influence or too many agents, then your models have these chaotic behaviors, and the resulting loss is also very large. So let's go back to, and this result kind of connect back to our initial examples. First, in the navigation app examples, our results suggest that if you have too much influence, that is, if too many drivers follows your recommendations, you are effectively increase your influence on the data distributions. And in that case, chaos may happen. For the credit score settings, if more and more banks using the same ways to evaluate the loaners, you are increasing the number of agents, learning agents in the systems, then you have a larger N, and then our results suggest chaos may also happen. For the police patrol examples, if your police departments rely more on the same machine learning algorithms, you are increasing your lambdas and chaos may also happen. And I think there's a lot of open question to think about the whole things. That is, once you have this dynamic of learnings, we may want to ask, how can we avoid chaos? Whether you have a better algorithms, because sometimes it's hard for you to coordinate multiple agents in the process, and can you have a synchronized ways to organize everyone. On the other hand, you can think of whether we can have a good mechanisms. That is, if you are governments or regulators, how can you avoid these chaotic results happens? And finally, whether we can have a more first principle way to model situation of preventive prediction.